All right, assalamu alaikum, everyone. Let's begin. So, in our last session, we completed the two major concepts that we have in normal distribution. There's one thing that is still left, that is binomial to normal approximation. However, we're done with the major part of the topic. We will be doing a couple of practice questions today, and then tomorrow we will be doing that last concept, and then do some more practice questions on Wednesday before we finish our S1 exam, S1 paper, inshallah. So what have we done in normal distribution until now? We've talked about how the normal distribution looks like, the curve, how it's symmetric, how the area under the graph is 1, and how we calculate probabilities using this curve. There are two types of questions that we have looked at until now. One is where you have some probability given. So where you have some data given. You have some value of x. You want the probability of x being less than something or greater than something or between some values. You have the mean given. That means the mu is given. You have standard deviation given. You have all of these things given. And what you need to find is the probability for that particular case that is required. Okay. Now, how do you do that? You first convert x to z. That's the first thing you do. You write x in terms of z, and then you convert it to the standard form that you can use the table for probability of z less than something positive, and then you can just use the table to find that probability, and that gives you the result. All right. So that's one idea. That's one type of question that you get in this. Then the next thing is that we did in the last class, we talked about inverse normal. So sometimes what happens is you have some missing data and you're given a probability. All right, so probability would be given and something from the data would be missing. You might have x missing or mu missing or sigma missing. You'd have to find that value. All right. Now for this, we had these steps that we looked at in detail in the last session. So first thing that you have to do is you have to figure out, you have to write the probability in terms of z and then figure out whether z is positive or negative. Once you figure that out, you convert it to the standard form that you can use the table for, probability of z less than some positive number. Then you use the table to find the value of z and then assign it a positive or negative sign based on what you did in step 1. Once you're done with that, use the formula z equals x minus mu over sigma to find any unknowns that you have. So you'll have the value of z. One of these three things might be missing, which you can figure out, or maybe two things might be missing. In that case, you'll have two pieces of information given and you'll have to solve some simultaneous equations in that case to find the values of those two unknowns. All right, so this is what we did in the last session. So these are two concepts that we have in normal distribution. Now, before we move on and do the last concept, which we'll actually do tomorrow, inshallah, let's do a couple of practice questions from the worksheet. I'm going to start with this one. This is question number 39 from the worksheet. Let's have a look at this. The first part is relatively easy. We'll see the second part. This is question number 39 from the worksheet. Let's try this. It says, it's given that y follows normal distribution with mean 33 and variance 21. All right, remember this notation? The first number stands for the mean and the second number, variance. We need to find the value of a given that the probability of y being between 33 minus a and 33 plus a is 0.5. Now, let me write that here. So we have another variable y now. This is part B. This variable y is normally distributed with mean 33 and variance 21. Let's write this on the side here. Mu is 33 and variance is 21. What about the standard deviation? That would be square root of 21. And we're given a piece of information here that the probability of y being between 33 minus A and 33 plus A is equal to 0.5. This is a probability that we're given. All right. Y is between 33 minus A and 33 plus A. We need to find this probability. Sorry, the probability is given. We need to find the value of A using this information. Yes, we need to find the value of A given this information. Now, again, we have probability given, and we have something missing in the data. So this is inverse normal. Remember what we used to do for inverse normal? We would first convert to Z and then figure out whether Z is positive or negative and then convert it to standard form. But the problem here is we have an interval. We have an interval like this. So interval cannot be read directly from the table. So it's going to be slightly more complicated to convert it to the standard form, first of all. What we can do here is we can first convert it to Z and see what these values here correspond to when written in terms of Z. Remember the formula? Z equals X minus mu over sigma. That's the formula that we have that connects Z and X. Now, in place of X here, we have Y. So we could just replace it with Y, right? So it's just any variable. So this could be Y. We could write this thing as probability of Z between Y minus mu. So see, Y here is 33 minus A. Minus mu. What's mu? Mu is 33. So we have 33 here. 33 minus A minus 33 divided by sigma. Sigma is square root of 21. On the right side, we have 33 plus A as the value for Y. So it becomes 33 plus A minus mu. Mu is 33 divided by sigma. Sigma is square root of 21. Now we have converted this to something in terms of Z. Now let's simplify this first. 33 and minus 33, they get cancelled. On the left side, we have minus A over square root of 21. And on the right side, we have plus A over square root of 21. This probability is equal to 0.5. So we have converted that probability that was in terms of Y earlier to something in terms of Z now. This is equal to 0.5. Now, let's try to understand this and see how we can convert it to the standard form. Now, remember what the normal distribution curve looks like. This is how the curve looks like. All right. Z needs to be between minus A over square root of 21 and plus A over square root of 21. Now, remember, these numbers are equal. So, for instance, in terms of magnitude, they're equal. For instance, on the left side, if we had 1.25, on the right side, we have plus 1.25. So their magnitudes are equal. Keep that in mind. So if I were to represent these numbers here on this curve, I could say if minus A over square root of 21 is here, on the other side, plus A over square root of 21 would be exactly at the same distance from the mean, from the middle, from 0. They are both at the same distance on either side. And what we're given is that the area between them, they might actually be closer. So that's 0.5. So let's say they're here. But again, the distance from 0 is equal. And we know that this area between these 2 points is equal to 0.5. This is what we're given. That the area between these 2 points is equal to 0.5. This region is 0.5. Now remember, it's a symmetric curve. It's a symmetric curve. And we know that these numbers in terms of their magnitudes are equal. If the region in the middle is 0.5, how much is left? We have 0.5 left. Now, since the curve is symmetric, that 0.5 is going to be divided equally in this region. This is going to be 0.25. And the other region on the right side, that's also going to be 0.25. Why? Because these magnitudes are equal. So on the right side, you have the same area as the left side. The remaining area is 0.5. You divide 0.5 by 2. So each of those areas is going to be 0.25. All right. Now, remember, in order to be able to use the table, you need the standard form. And what does the standard form look like? It's z less than a positive number. That's what the standard form is. The standard form is probability of z less than a positive number. That is what you have to use for the table. So what we can do is, we can write this thing as, so if you look at the graph, look at the curve, we could say the area to the left of a over square root of 21, how much is that? It's 0.5 here and 0.25 here. The total area to the left of a over square root of 21, that is 0.75. So if we know that the probability of z being between these two values is 0.5, this implies that the probability of z being less than a over square root of 21, how much is that going to be? 0.5 plus 2.25, and that gives us 0.75. And this is something that is now in the standard form. It's z less than a positive number. And now we can go to the table and figure out the value of z here. So this is what we need to figure out. We know that the area to the left of 0.75 is, the area to the left of this value is 0.75. We need to find the corresponding value of z for this. All right, let's go to the table. The probability is 0.75. Let me write that here. The probability is 0.75. So we could write it as 7500. Remember, probabilities are generally written to 4 decimal places here. 0.7500. Where is that? Okay, so I have 7486 here. 0.7486. What I get from this is z equal to 0.67. And then how much do we need to add here? 14. We go to the right side and see where 14 is. 14 is not here. However, 13 is the closer number. So this third decimal place is going to be 4. So that's 0.674. That's the value of z that we get from this. 0.674. Now, just to let you know about this, there is a small table given at the bottom here in which you have some common probability values for which you have the z values given directly. And 0.75 is actually one of these common values that's used more commonly in practice. So in order to make things simpler, they have given these probability values and their corresponding z values separately here as well. So the 0.674 that you found here from the table, in this case, and only in this case, where you have probability 0.75 or one of these other cases, you could find this value from this smaller table at the bottom as well. That would give you 0.674. It's coming from the same big table, but they've written it separately to make things easier because it's used a lot in practice. So Z value is 0.674. Let's go back there. We say that this value is 0.674. And that gives us that A over square root of 21 should be equal to 0.674. Square root of 21 goes to the other side, gets multiplied with 0.674, and that is going to give you the value for A. Let's figure that out. 0.674 into square root of 21, that gives me 3.089, and that's the value of A that we were looking for. All right. Any quick questions on this? Any problems?
No, sir.
Okay, let's have a look at another one. And then tomorrow we will be doing binomial to normal approximation inshallah, and then we'll spend another session on Wednesday, which might be the last session, unless you have any questions on any topic. In that case, we could have another class on Thursday as well to just discuss those practice questions, those questions that you have. Okay, now let's do another one before we end. We'll do a few more difficult ones on Wednesday, inshallah. Let's do one more today before we end. This is question number 53 from the worksheet. Let's have a look at this. You can also come with your questions from the worksheet or from any recent paper. If you have any on Wednesday and Thursday, we can discuss those questions on those days. For now, I'm just choosing some questions, which if you understand them, it might make the rest of the worksheet easier because it covers almost everything that you need to know. Okay, this is question number 53 from the worksheet. Let's have a look at this. It says the lengths of body feathers of a particular species of bird are modeled by a normal distribution. A researcher measures the lengths of a random sample of 600 body feathers from birds of this species, and finds that 63 are less than 6 centimeters long and 155 are more than 12 centimeters long. Find estimates of the mean and standard deviation of the lengths of body feathers of birds of this species. Okay, now let's break it down. Let's try to make it simpler. So what are we talking about? We have lengths of body feathers. They are modeled by a normal distribution. So lengths of body feathers, this is actually the variable, the length of body feathers. This follows normal distribution. Let's call this length X. A researcher measures the lengths of a random sample of 600 body feathers from birds of this species and finds that 63 are less than 6 centimeters long and 155 are more than 12 centimeters long. What we can infer from that is, since we have a sample of 600, out of them, 63 are less than 6 centimeters long, using the concept of relative frequency. We could say the probability of X, the length of a body feather, being less than 6 centimeters long. What would that be? Out of 600, 63 satisfy that condition. So that's 63 over 600. Favorable outcomes divided by the total number of outcomes, 63 over 600. And that gives us that the probability of X less than 6 is equal to 63 over 600. Let's evaluate this. This turns out to be 0.105. Now, what else are we given? Out of this 600, 155 are more than 12 centimeters long. So that means probability of X being greater than 12, that is equal to 155 over 600. We can evaluate this as well and see what that gives us. Probability of x greater than 12 is equal to 0.2583. That's what we get from this. So we have two pieces of information given here. Both are probabilities. We need to find, in the first part, estimates of the mean. That means we need the mu and standard deviation, sigma, of the lengths of body feathers of birds of the species. So we need to find mu and sigma. All right, so this is simple inverse normal distribution. Let's do this quickly. How do we start? We just write it in terms of z first of all. So it's the same as z less than something equals 0.105. And we need to figure out whether z is positive now or negative. Let me copy a curve from this, from here. For that purpose, you can just draw a rough sketch quickly. Okay, so this is what I have. What we're saying is area to the left towards left of this value of z should be 0.105. Is that smaller than 0.5 or greater than 0.5? That's smaller than 0.5. So the area to the left should be smaller. So if we place z here on the negative side, then we have less area on the left side. So z has to be negative, right? Because that would make sure that the area to the left is less. It's smaller. So z has to be negative. We can write that here. We have figured out that z should be a negative value. Okay, so this is important. Now, we are given that this area here is how much? This is 0.105. Now, this is not something that we can find directly from the table because it's not the standard form. Z is negative. We need to make it positive and then have the standard form z less than a positive number. So what we can do is we can say, let's flip this. If the area to the left of this negative value is 0.105, if we consider the corresponding positive value of z on the right side, so for example, if this was minus 1.5, if we consider 1.5 on the right side, that's what we're saying, then to the right of that value, we would have the same area. This area would also be 0.105. And if this area is 0.105, what about the area to the left of this value? Because that is going to give us the standard form. It would be 1 minus 0.105. So what we can say here is, we can say probability of z being less than this positive value z is equal to 1 minus 0.105. You can see what that is, 0.895. So we have converted this to the standard form now. And once you have done that conversion, now we can find the value of z from the table. Let's see what we get from that. 0.895. Let's go to the table and see what we have. 0.895. Zero 0.8950. Okay, so we have 8944. 0.8944. What value z are we getting from this? 1.25. And then how much do we have to add more? 6. We go to the right side. This is where 6 is. The third decimal place, therefore, should be 3. So that's 1.253. That's the value of z that we have. But now we need to be a bit careful. What we have got here is the positive value of z, which is 0.25. Oh, no, sorry. You go back there. It's 1.253, not 0.253. 1.253. But remember, the actual z is negative. We have figured that out before. The actual value of z is supposed to be negative. So z is therefore minus 1.253. So when you input this value in the formula, you should be inputting minus 1.253 there. All right, let's apply the formula. Z equals x minus mu over sigma. Z is minus 1.253. The corresponding value for x that we have here is 6. 6 minus mu over sigma, and that gives us minus 1.253 sigma equal to 6 minus mu. This is one equation that we have. So in the second equation, what we have is that the probability of x greater than 12 is equal to 0.2583. That's the other piece of information that we have. Now, we do the same thing here. We convert it to z first, so it becomes probability of z greater than something that is equal to 0.2583. And again, we need to figure out whether this value of z is positive or negative. We do that using this curve again. Okay, so now what does this say? It says area to the right, area towards right, that should be smaller. If you compare it with 0.5, it should be smaller than 0.5. So now what we want is that the area to the right of this value of z should be smaller. Where do we place z here? We'll have to place it on the right side, because that would ensure that the area to the right of z is smaller. So this area that we have, this is equal to 0.2583. All right. Now, this is not the standard form. So in order to convert it to standard form, we would have to write it like this. We would say the area to the left of this value is going to be 1 minus 0.2583. So we could write this as probability of z less than the positive value of z. Remember, the actual value of z is also positive. All right, so z less than that positive value, what's that? 1 minus 0.2583. Let's figure that out. Let's see what that turns out to be. It would be 0.7417. Now, this is the standard form. This is the probability that you have. You can go to the table and figure out the corresponding value of z for this. 0.7417. This is the table. Now we're looking for 0.7417. 0.7417. Let's look for this value. This is the immediately smaller value, 7389. The corresponding value of z that we have from this is 0.64. And this corresponds to 7389. Now, how much more do we have to add? 11 plus 17, which is 28. We need 28 more. We go to the right side here. We have 28 here. We don't have 28, but 29 is closer to 28. So we use 29 here. And the corresponding value is 9. So it's 0.649. That's the value of z that we have here. Z is equal to 0.649. All right. Now, since z was supposed to be positive, we just keep it as it is. That's the value of z. We input this in the formula. The formula is z equals x minus mu over sigma. Just input values in this, and that will give you the result. So that's 0.649 equal to the corresponding value for x is 12. So that's 12 minus mu over sigma. And this gives us 0.649 sigma equal to 12 minus mu. You have two equations now. You can solve them simultaneously to find the values for mu and sigma. All right, so that's what we had to do here. Let's solve them simultaneously now. We could make mu the subject in both of them. So this gives us 6 minus 6 plus 1.253 sigma, and the other equation can give us mu equal to 12 minus 0.649 sigma. Equate both of them, and that gives you 6 plus 1.253 sigma. That equals 12 minus 0.649 sigma. Solve this and you get the value for sigma from this. Just take the sigma terms on one side, everything else on the other, then do the division. This is going to give you sigma equal to 3.155. All right, so that's one value that we were looking for. Put this back in any one of those two equations, and that will give you the corresponding value for mu. So that's 6 plus 1.253 into 3.155, and that will give you the corresponding value for mu. Let's see what that turns out to be. This is 9.95. That's the mean of this distribution. These were two things that we were looking for here, and we've written them down here. Okay, mu and sigma, we found those two values. All right, let's look at the second part of this. Now, the second part says, in a random sample of 1,000 body feathers from birds of this species, how many would the researcher expect to find with lengths more than one standard deviation from the mean? Okay, now let's think about this. In a random sample of 1,000 body feathers, how many would the researcher expect to find with lengths more than one standard deviation from the mean? Let's find this probability first of all. Probability of a body feather having length more than one standard deviation away from the mean. Because once we have this probability, we would know that for one body feather, this is the probability. Then what about the expected number in 1,000 body feathers? We could just multiply that probability with 1,000 to get that number. Okay, so first thing we need to do is we need to figure out the probability of this condition being satisfied. All right, length more than one standard deviation from the mean. Now think about this. Let me give you an example first of all. So let's say the mean is for a distribution, let's say the mean is 7 and the standard deviation is 2, let's say. What does it mean to be more than one standard deviation from the mean? What it means is you should either be less than 5 or greater than 9. All right, so if we were to represent this on a number line, you have 7 in the middle. So you need to be more than one standard deviation from the mean. What's one standard deviation? One standard deviation is 2. So that means you need to be more than 2 units away from the mean. So you either are to the right of 9 or to the left of 5. That's what it means. Okay. Now in this particular case, we have found the mean and standard deviation already in the first part. Mean is 9.95 and the standard deviation is 3.155. All right, what it means now is if the mean was in the middle here, let's say it was 9.95. In this case, it is 9.95. One standard deviation from the mean means you subtract. So basically, you want to be more than 3.155 units away from 9.95. So subtract 3.155 from 9.95. Let's see what that gives you. Let's do this subtraction. This would give you 6.795. So you either have to be to the left of this value, all right, or more than 3.155 units away on the right side, add 9.95 to 3.155. That would give you 13.105. So you could be on this side. This is a probability that you need to figure out. Either less than 0.6795. So probability of either being less than 6.795. Sorry, 0.6795. No, that's actually fine. 6.795. Or the probability of x being greater than 13.105. We need to find these two probabilities, and this, since there's an or between them, we just add both of them then. All right, now let's convert it to z, and once we do that, you'll actually realize something that we discussed in the very beginning when we started normal distribution. If you remember that, you could actually do this quicker, but let's do this quick. Let's do this first. How do we find probability? Now remember, this is simple normal distribution. It's not inverse normal. You have to find the probability. You have data given, you have to find probability. What do you do for this? You first convert it to z. Remember the formula? Z equals x minus mu over sigma. Apply that formula first of all to convert this probability to something in terms of z, because in the table we only have z values. So we could write this as probability of z less than 6.795 minus the mean. Mean is 9.95 divided by sigma, which is 3.155. And this is actually going to turn out to be z less than -1. All right, because the difference is 1 here on the negative side. So it's the difference is 1 standard deviation, and you're dividing this by standard deviation. It turns out to be 1 on the negative side. So it's -1. Similarly, if you were to evaluate this other one, z greater than 13.105 minus 9.95 divided by 3.155, that would give you z greater than 1, because this is more than 1 standard deviation on the right side. Okay, so you just have to find these two probabilities and add them together. Now, if you remember, the interpretation of z values, you could actually write this directly, and you would not have to do all of this thinking that you did before. How exactly would that be possible? Remember what we discussed about z values when we started normal distribution? Z value here represents the number of standard deviations the value of x is away from the mean. So we looked at this example. If you remember, mean was 5.4, standard deviation was 0.4. If we have a value of 5.6 here, or let's take another, in fact, let's say 5. 5 is 1 standard deviation below the mean, 0.4 less than the mean. That's why the value of z that we have here is -1. All right, because it's 1 standard deviation below the mean. Similarly, 5.8 is 1 standard deviation above the mean, so the value of z here is 1. So the z value represents the number of standard deviations you are away from the mean. In this case, what does the question say? The question says the length should be more than 1 standard deviation away from the mean. So you could just use z here directly. You could say in z distribution, there's 0 in the middle. 1 is the standard deviation. So you should either be to the right of 1 or to the left of -1. All right, and you can just write this directly without doing any calculation in terms of X earlier. You could just think of it in terms of Z directly. Okay, that is also possible. Anyway, let's say you're done with this now. Now we need to find this probability. How do we do this? We have this normal distribution curve. What probabilities are we looking for? We are looking for the probability of Z being less than -1. So if this value is -1 and this value is +1, what we're looking for is the area to the left of this value plus the area to the right of this value. These are two areas that we're looking for. Now, since the curve is symmetric, we could actually just find any one of the two and multiply that by 2. All right, so we could find any one of these two areas. Let's find one of them. You could say, for instance, let's find probability of Z greater than 1. That will be this area. You can't find that directly from the table. You have to convert it to standard form. It would be 1 minus probability of Z less than 1. Now, this is the standard form. This is something that you can find from the table. Z less than 1, right? So the Z value is 1. Let's go to the table and see the probability that we have corresponding to the value of 1. This is a Z value of 1. The probability is 0.8413 here. So we write 0.8413 here. This turns out to be 0.1587. This is the probability of Z greater than 1. So we have one of these shaded regions. What about the other one? That's going to be the same as well. So the total probability is just 2 times this. The total probability in this case would just be 2 into 0.1587. Let's see what that turns out to be. This is 0.3174. All right, so for one body feather, what's the probability that the length is 1 standard deviation, more than 1 standard deviation away from the mean? For one body feather, the probability is this. What about 1,000 body feathers? Out of 1,000 body feathers, what would be the expected number that satisfies this condition? You would just say 1,000 into 0.3174, and that's going to give you 317.4. Now, since we're talking about body feathers, they can't be in decimals. It's better to write it as an integer, just round it off. When you round it off, it will become 317, and that is going to be your final result here. Okay, so remember, we were talking about 1,000 body feathers here. So out of 1,000, how many would you expect to find with lengths satisfying this condition? We have the probability of 1 body feather satisfying the condition. What would be the expected number with 1,000 body feathers? Just 1,000 multiplied by that probability. You could also think of it as a binomial distribution, by the way. We have 1,000 body feathers. So you could say, so another way of thinking about this could be, you could say this is the outer distribution is a binomial distribution with n equal to 1,000. The probability of success would be 0.3174, and the probability of failure would be 1 minus this. And then what's the mean or expected value of a binomial distribution? For a binomial distribution, the expected value is n times p. And that's why we're doing that, 1,000 into 0.3174. And that will give you the same thing, which is 317. That could be another way of thinking about this using binomial, or you could just use your logic and multiply this directly like this. So that's the expected number that you would find, that you would expect to find satisfying that condition. All right, I hope that makes sense. You're going to stop it here. In our tomorrow's class, we'll be doing the last concept that we have in normal distribution. And with that, we will finish our syllabus, inshallah. And we will do one more class, at least, on doing some more practice in normal distribution on Wednesday, inshallah. You can come with your questions as well. And then if there are any other problems on any of the other S1 topics, we could have another class on Thursday before we wrap things up. All right, that's it. I'll see you again tomorrow. If you have any quick questions, let me know. Otherwise, we end it here.